Hey everyone, you know that feeling when you're deep into a massive puzzle, like a Sudoku or some complex logic problem, and you realize one wrong move way back at the beginning has messed everything up? It's so frustrating. Well, today, we're going to crack the code on two amazing algorithmic techniques that are built to handle exactly those kinds of tough computational challenges.
Okay, picture this. You're dropped into a gigantic maze. Thousands of possible paths, forks in the road everywhere, but only one of them actually leads out. So how do you find it without just wandering around forever? That's really the core challenge for so many problems in computer science, navigating this huge state space of possibilities to find the right answer.
So, in this explainer, we're going to demystify two really powerful strategies for finding your way through these kinds of mazes: backtracking and branch and bound. Seriously, you can think of them as the ultimate map and compass for solving some of the toughest puzzles out there.
All right, let's jump right in with our first tool, backtracking. The best way to think about this one is to picture a really methodical, super careful explorer. It's going to systematically check every single path, one step at a time, until it finds any solution that works, as long as it follows all the rules. The key here isn't about being fast. It's all about being thorough.
So, what's the official definition? Well, backtracking is a technique built for what we call constraint satisfaction problems. Fancy name, but it just means puzzles where your answer has to follow a very specific set of rules, or constraints. You try to build a solution one piece at a time. And here's the magic. The moment you place a piece and it breaks a rule, you don't throw everything out, you just backtrack. You undo that one last move, and you try a different one. Simple as that. You know, the logic behind it is actually pretty elegant. It really boils down to a simple loop. First, you try a move. Then you check it. Does this break any rules? If it's all good, you continue. You go deeper. But if it's invalid or you just hit a dead end, that's when you backtrack. You undo that move and try another option. It's this constant cycle, a recursive journey that explores every possibility.
Okay, so a perfect example to see this in action is the classic 8 queens problem. The idea sounds simple, right? Just place 8 chess queens on a chessboard so that none of them can attack each other. But actually doing it, well, that's a whole other story.
So how would backtracking solve this? Well, you'd start by placing a queen in the first row. Easy enough. Then you move to the second row and find a spot where it's safe. Then the third, and you keep going. But let's say you get to row 5, and oh no, there are no safe squares left. This is where backtracking shines. You don't panic, you don't start over, you just backtrack. You go back to the queen in row 4, move her to the next safe spot, and then you start moving forward again. It's that simple.
So if you take away one thing about backtracking, it's this. It's all about diving deep down one path, exploring possibilities, and having a built-in, smart way to retreat from dead ends. It's an explorer that knows when to turn back. Okay, but that brings up a really important question, doesn't it? The 8 queens problem just wants any valid solution. But what happens when any solution isn't good enough? What if you need the best one? You know, the shortest route, the cheapest option, the absolute maximum value? For that kind of problem, we're going to need a different tool. And that leads us right to our second algorithm, branch and bound. So if backtracking is our systematic explorer, then branch and bound is the super smart optimizer. It's built from the ground up for optimization problems, where finding just any old answer is a failure. You need the absolute best. The name pretty much tells you everything you need to know. It branches out, exploring a tree of possible solutions, a lot like backtracking does. But, and this is the really genius part, it also calculates a bound for each branch. Now, this bound is just an estimate, a best-case scenario guess for that path. And it uses that guess to intelligently prune or chop off entire branches of the search tree that it knows can't possibly lead to the best answer. And right here, you can see the key difference in how they think. Backtracking just asks, is this move allowed by the rules? It's a simple yes or no. But branch and bound adds a second crucial question. Okay, this move is valid, but is there any chance it could lead to a better result than the best one I've already found? If the answer to that is no, it just prunes the whole branch. It's a strategic move that saves an incredible amount of time and effort. Now, if you want the poster child for branch and bound, look no further than the infamous Traveling Salesman Problem, or TSP. This thing is a notoriously difficult puzzle to solve.
The goal, right, is to find the absolute shortest tour that hits a bunch of cities and comes back home. So here's how Branch and Bound attacks it. It branches by picking a next city to go to. Then it calculates a bound. That's the distance you've already traveled, plus a really optimistic guess for the rest of the trip. And here's the prune part. If that total estimated distance is already longer than a full tour you found before, you just throw that path away, right? Why waste time on it if you know it's already a loser?
What's cool is that branch and bound is way more flexible than backtracking. It's not stuck with just one way of searching. It can do a breadth-first search, we call that FIFO, which eats up more memory but might find a good solution faster. Or it can do a depth-first search, like LIFO. But the real powerhouse strategy is called least cost. It uses what's called a priority queue to always check the most promising-looking path first. It's like it has an instinct for where the best solution might be hiding.
Okay, so now we've got our two heavy hitters. Let's put them in the ring for a little showdown, just to make it super clear which tool you should grab for which job. So let's break this down. First up, problem type. Backtracking is your go-to for constraint satisfaction problems. Can I find a solution that follows the rules? Branch and bound is for optimization. What's the best possible solution? And that directly leads to their goal. Backtracking is happy finding any valid solution, or even all of them. Branch and bound has one mission: find the single best, the optimal solution. And finally, their pruning method. This is huge. Backtracking only stops when a rule is broken. Branch and bound is way smarter. It stops exploring a path the second it knows it can't possibly be the best one. All right, so this all sounds a bit academic, right? Puzzles and chessboards. But why should you care about this stuff in the real world? Well, because these algorithms are absolute game changers for solving massive, practical problems. I'm talking about the engines that power huge logistics companies, figuring out the best delivery routes to save time and fuel. They're used to schedule airline crews for thousands of flights, a crazy complex puzzle with tons of rules and regulations. Basically, anywhere you see complex resource management or operations research, you can bet these ideas are working hard behind the scenes. And here's the big takeaway, the thing I really want you to remember. In the worst case scenario, yeah, these algorithms can be super slow, but their real power, that comes from how you implement them. A really clever pruning strategy or a super tight bound. That's what can turn a theoretical, impossibly slow algorithm into a practical tool that actually solves real-world engineering problems. So, there you have it. You've now got two of the most essential search and optimization strategies in your toolkit. You had the systematic explorer for finding any solution and the smart optimizer for finding the best one. The only question now is, what complex, real-world problem are you going to solve first?